Hello to everybody and welcome to the third lecture of Heat and Mass Transfer MHM 42780. In this lecture we are going to speak about the radiative property of real surfaces. We are going to speak about emissivity, reflectivity, transmissivity and absorptivity. We are going to speak about Krishov's law, and we are going to talk a bit about solar radiation as well. If you remember, during the last two lectures, I talked about Blackbody, and I told you that Blackbody is an ideal model, and if it's not impossible, it's very difficult to get the Blackbody. So you might say that, okay, why then we study Blackbody when it's very difficult to get and it's completely different from the real surfaces. The fact is, to define the radiative property of real surfaces, we can use Blackbody concept. We know that Blackbody is an ideal emitter in the sense that no surface can emit more than a Blackbody at a given temperature. So it is convenient to use Blackbody as a reference in describing emission from a real surface. For example, let's say I want to define a concept called emissivity. I can use the concept of Blackbody into it. So I can say that, okay, emissivity of a surface can be defined as a rate or a ratio between radiation emitted by a surface divided by radiation emitted by a Blackbody at the same temperature. Okay? Very simple. But you see in this picture that emissivity of a real surface is not a constant, and it may be have different values according to whether the one is interested in emission at a given wavelength or in a given, like a temperature direction. So to sort all those problems out and to address them, we are going to define 4 different concepts for emissivity. So first, we speak about spectral, directional emissivity. Okay? We also will speak about the total directional emissivity. We will speak about the spectral, hemispherical emissivity, and we are going to talk about total hemispherical emissivity or average emissivity. Okay, this is shown by epsilon, lambda and theta. So of course it's a function of epsilon, theta, phi and temperature. So I lambda E lambda theta phi T divided by lambda B lambda and T. So intensity of radiation, the wavelength of theta to the intensity of radiation emitted by a Blackbody. Epsilon theta, which is the total directional emissivity, it's theta phi T divided by emissivity of black body. But in practice, for most engineering calculation, it is desirable to work with surface properties that represent directional average. So for spectral hemispherical emissivity, lambda, which is a function of lambda and t, so we have E lambda and t divided by E B lambda, black body, lambda and t. And this one is a function of course, lambda theta and not theta and phi. Okay? And t. And total hemispherical emissivity or average emissivity is just a function of t, so Et divided by Eb t, which is equal to sigma T4, 0 to infinity, epsilon lambda, lambda t, Eb lambda t d lambda. Okay. That's the four different concepts that we define for emissivity, but normally we use average emissivity anytime that you see in the like a question that it's asking for average emissivity. It means that it's the total hemispherical emissivity. Okay, let's assume that we have a real surface and this picture is showing the emissivity function of our real surface. So we have a kind of a step function to define the emissivity of this surface. So 3 boundaries between lambda 1 wavelength is epsilon 1, wavelength between lambda 2 and lambda 1 and lambda 2 is epsilon 2, and for wavelength greater than lambda 2, lambda 2, it's epsilon 3, like a step function. How we are going to calculate the average emissivity? Average emissivity, epsilon t. If you remember, we said that average emissivity is Et divided by Ebt, so the black body. So basically we can say that, okay, it's Ebt here will be integration between 0 to infinity, epsilon lambda t, Eb lambda t d lambda. Since there are constant for different boundaries, we can take it out from the integration. So it's epsilon 1, 0 to lambda 1, Eb lambda t d lambda divided by Ebt plus epsilon 2 between lambda 1 to lambda 2, Eb lambda t d lambda Ebt plus epsilon 3 between lambda 2 to infinity, Eb lambda t d lambda divided by Ebt. But you remember what is this? We defined that it's black body radiation function. Yeah, you remember that function. So if I want to write it based on the black body radiation function, I can write it as follow. So the epsilon t is equal to epsilon 1 function between 0 to lambda 1 plus epsilon 2 function lambda 1 to lambda 2 plus epsilon 3 function lambda 2 to infinity. Yeah, epsilon 1 black body radiation function between 0 to lambda 1, epsilon 2 multiplied by black body radiation function between lambda 1 and lambda 2 plus epsilon 3 multiplied by black body radiation function between lambda 2 and infinity. Okay. Normally we are interested in four different surfaces, and I'm going to speak about these different surfaces in terms of emissivity. So here you see that for blackbody is the first surface of interest. The blackbody emissivity is equal to 1. So the blackbody emissivity is equal to 1. Anytime that you see in a question that I said the blackbody, immediately you can say that, okay, emissivity is equal to 1. The second surface of interest is diffuse surface. For diffuse surface, epsilon theta is constant. What does it mean? It means that emissivity is independent of direction. The third surface of interest is gray surface, and for gray surface epsilon lambda is equal to constant, is a constant. Why? Because the emissivity is independent of a wavelength. And the fourth one, which is a real surface, for real surface neither epsilon theta nor epsilon lambda are constant. Okay. Now it's time to speak about the other radiative properties of material. Now we need to speak about absorptivity, reflectivity, and transmissivity. What can happen when radiation strikes a surface? We have an incoming beam of irradiation hitting a surface. What can happen to it? Three things can happen. It can reflect, it can absorb, and it can be transmitted. So irradiation strikes a surface. How much of that will be reflected? A portion of it we called rho g. What is rho here? Is reflectivity. Dimensionless number between 0 and 1. If irradiation strikes a surface, how much of that irradiation will be absorbed? Alpha g, portion of it. What we call alpha? Absorptivity. And the same will happen here as well. Irradiation strikes a surface. How percentage of that one will be transmitted? A portion of it, we call it tau g, which is tau is transmissivity. Okay. All of them, reflectivity, absorptivity, and transmissivity, are dimensionless numbers, and their value are between 0 and 1. Okay. So we said that the G, like irradiation strikes, it will be either reflected or absorbed or transmitted. So equal to rho plus alpha plus tau g. Then we know that rho plus alpha plus tau is equal to 1. It's very important relationship between reflectivity, absorptivity, and transmissivity. Okay, so we know that. Now let's apply it and to see how this correlation will work for different surfaces. First, let's say blackbody. we have a black body surface. What does it mean? For the black body, alpha, which is absorptivity, is equal to 1. So if absorptivity is equal to 1, because it's a perfect absorber, alpha is 1, rho needs to be equal to tau is equal to 0. So immediately when we hear black body, alpha is equal to 1, emissivity is equal to 1, rho is equal to 0, tau is equal to 0. The second one is for opaque surface. Opaque surfaces such as most solids and liquids. Anytime in this course when you see like a solid surface, we don't mention anything about it, about the transmissivity, absorptivity, reflectivity, you can assume that it's opaque surface. For opaque surface, tau, which is transmissivity, is equal to 0. So finally we end up by having reflectivity plus absorptivity is equal to 1. So those two surfaces are really important that we need to keep in mind. We also, it's good to know that for gases, the reflectivity is equal to 0. So we will have absorptivity plus transmissivity is equal to 1. We need to know that these definitions that we presented here for reflectivity, absorptivity, and transmissivity, all of them are for total hemispherical properties or average properties, since irradiation represents the radiation flux incident on the surface from all directions for all the wavelength. Okay? But now look at this picture. It shows the spectral dependence of the spectral and normal absorptivity as well as reflectivity for some materials, mostly opaque. If you look at this picture, it's completely obvious that determination of radiative properties of real materials is not actually very easy, because it may be characterized by both directional or spectral dependency. You see that sometimes it goes up and after that it sharply goes down. For that reason, we can define some like spectral directional absorptivity, reflectivity, or transmissivity. Let me just write it down for you to have it. So spectral directional properties. So alpha, lambda, theta and phi is equal to lambda absorb, lambda, theta and phi divided by I lambda incident, lambda, theta and phi. For spectral directional reflectivity, we have the theta, lambda, theta and phi is equal to I lambda and reflected, lambda, theta and phi divided by incident. The same can be extended to transmissivity. We can also define the spectral hemispherical properties as well. It is for absorptivity, we have E lambda is equal to G lambda and absorptivity lambda divided by G lambda. for reflectivity, we have G lambda and reflected divided by G lambda. We can also do the same for transmissivity. Tau lambda lambda is equal to G lambda transmitted divided by G lambda. And finally, we know that by integration over the wavelength we will have the average radiative properties. So average radiative properties, or total hemispherical properties. So for T is integration between 0 to infinity alpha lambda G lambda d lambda divided by 0 to infinity G lambda d lambda. And in the same way we can do it for reflectivity as well. So it's 0 to infinity G lambda d lambda divided by infinity G lambda d lambda. Okay. Now let's solve a question and see how we can use this concept in action. This is the question 12.77 of your textbook. The reflectivity of aluminum coated with lead sulfate is given. So if you remember, I told you anytime when we see any solid, we can say it's opaque. Okay, that's an opaque surface. We have some information, and what we is asking us is determine the emissivity, absorptivity, and at the end is asking if this surface is suitable for use in solar collection. Okay, so as I told you, we can follow the same path as the previous one. First, let's say what we got here. So what we have is we have the reflectivity based on the wavelength. We say that for 35 if and there is 3 meter, and it's like a kind of a step function for 0.95. What we need to find is rho t, epsilon t, and if it's suitable for absorptivity, and if it's suitable for solar collector. Okay, we need to find these stores. Okay, let's start. So for a step function, it's easy to say that. So it's 1 f1 to 0 to lambda 1 plus 2 f lambda 2 to infinity. So for this one, of course, we can say that 0 to lambda 1 to 1 minus f 0 to lambda 2. Okay, because we want to go and read it from the table. So in order to be able to read it from the table, we need to get the information from the table. So it's 0.35 0 to 3 micrometer plus 0.95 1 minus f between 0 3 micrometer. Okay, so now let's go to the table and read it. So the question is asking, if we go back, this question is asking determine the average reflectivity for two different temperatures. Okay, So we need to find it for two different temperatures. So let's use it here. So first temperature T is equal to 5800 Kelvin. So for this temperature, lambda T will be 3 micrometer multiply 5800 Kelvin is equal to 17,400 meter Kelvin. From this interpolation between for these two numbers between 16,000 and 18,000, we find that F0 to 3 micrometer for temperature of 5800 is equal to 0.978746. Okay, and for again we need these numbers from the table. For T is equal to 300 Kelvin, so lambda T will be 3 micrometer multiplied by 300 Kelvin. It will be 900 micrometer Kelvin. From here we need to do the interpolation between 800 and 1000, and the Blackbody radiation function between 0 and 3 micrometer for temperature of 300 Kelvin from the table will be 0.0001685. Okay, now by knowing these two numbers, we can just like put it into the equation. So rho T for temperature of 5800 Kelvin is equal to 0.35, 0.978746 plus 0.95, 1 minus 0.978746 is equal to 0.362. And the reflectivity for temperature of 3, it's 0.35, 0.0001685 plus 0.95, that 1 minus 0.0001685, it's equal to 0.95. Okay, so we find reflectivity. How about absorptivity and emissivity? What surface is that? Is opaque surface. Opaque surface. So tau is equal to 0, and we know that alpha plus rho is equal to 1. So alpha for or at 5800 Kelvin will be equal to 1 minus 0.362, which is equal to 0.638, and alpha at 300 Kelvin is equal to 1 minus 0.95 is equal to 0.05. So we find reflectivity, we find absorptivity, but the question is asking about emissivity as well. But there is no way to be able to relate this emissivity with the rest of radiative properties. We could relate absorptivity, reflectivity, and transmissivity, but how about emissivity? Okay, to do so we need to define a concept called Krishov Law. I'm going to go back to this example and finish it, but first we need to define it. So let's speak about Krishov's law. Okay, let's assume that we have several bodies inside a large isothermal enclosure. with the surface temperature of T. I'm sure you remember this large isothermal enclosure when I was speaking about the blackbody and the characteristics of a blackbody. I told you previously that this isothermal enclosure forms a blackbody cavity. Besides that, since the bodies inside the enclosure are small relative to the size of enclosure, their influence on the radiation fields is negligible. Therefore, the radiation incident on any part of the surface of those small bodies is equal to the radiation emitted by a black body of the temperature of T. Okay? So it will translate what I said, that irradiation is equal to emissive power of black body. Okay? Under a steady state condition, thermal equilibrium will achieve between bodies and enclosure. So T1 will be equal to T2 will be equal to T3 will be equal to T. So steady state thermal equilibrium. And the net rate of energy transfer to each surface must be 0. Why the net rate of energy transfer should be 0? You remember exactly. Why? Because the thermal equilibrium has achieved. So let's apply that energy balance here to one of the surface and apply that energy balance. So we can say that alpha 1 for surface 1, GA1 minus E1T A1 is equal to 0. Okay, we also said that the G is equal to EBT. So alpha EBT here will be alpha 1 divided by E1T. I deleted the A from both sides. Okay, so no question so far. It's like very simple thing. We didn't do any extraordinary thing. Okay, so now let's continue and see where we can get out of there. Since the result must apply to each of the bodies, we will have, so E1T divided by alpha 1 should be equal to E2T divided by alpha 2 should be equal to E3T divided by alpha 3. Why? Because all of them, they are equal to emissive power of black body. So you see here, emissive power of black body at that temperature is equal, so it's a constant. That's the reason is that all of them, they will be equal. Okay, so let's say here is alpha, 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 and alpha is absorptivity. You remember from emissivity what I told you? Emissivity is basically is E1 divided by EB. Am I right? So the emissive power of like a normal surface divided by emissive power of a black body. So if we implement it, we will have epsilon 1 EBT divided by alpha 1 is equal to epsilon 2 EBT divided by alpha 2 is equal to epsilon 3 EBT divided by alpha 3 is equal to EBT. So epsilon 1 EBT is equal to alpha 1 EBT. Epsilon 1 is equal to alpha 1, epsilon 2 is equal to alpha 2, and epsilon 3 is equal to alpha 3. As simple as that. So for any surface inside the enclosure, this relation is called Krishov Law and is valid. But there are 3 different forms of Krishov's Law that we are going to talk about it here. So first, epsilon T is equal to alpha T. We call it diffuse gray form of Krishov Law. Epsilon lambda T is equal to alpha lambda T. We call it diffuse form of Krishov's law, and epsilon lambda theta T is equal to alpha lambda theta T, and this is the exact form of Krishov's law. Okay, now if we go back to the example that we were talking about, so we have the reflectivity, we have the absorptivity, we know the transmissivity is 0. By having the absorptivity, we have emissivity as well. So from Krishov's law, say that alpha is equal to so alpha at 580 degrees, we say that it was equal to 0.638, and alpha at 300 Kelvin was equal to 0.05. So that will be the same as epsilon. If it's a good material for a solar collector, since it has a low emissivity at room temperature, yes, it is a good material for solar collector. Okay, so this section is basically done, but now we are going to speak about solar radiation. There is nothing that can I add to your understanding about the importance of solar radiation as the primary source of energy for us. We all know about it, but the energy coming from the sun passes through the Earth's atmosphere. Its magnitude and its spectral and directional distribution experience significant change. So it's not the same thing that leaves the sun. This change is due to absorption and scattering of radiation by the atmospheric component. This figure, you see that it's like shows in the 3 different colors, shows the effect of absorption by atmospheric gases, which are ozone, O3, vapor, H2O, oxygen, O2, and carbon dioxide, CO2. But it's like in the UV region, visible region, and infrared region. In the UV region, as you can see, the absorption by ozone is very strong. Okay, but in visible region there is some absorption by ozone and oxygen, and in the near and far infrared region the absorption is dominated by the water vapor. Okay, so I just wanted to show you, and if you remember the boundaries I was talking about, solar radiation between 0.4 micrometer to 3 micrometer that we call it solar radiation is between visible and infrared. Here you see that this is like the sun is nearly spherical radiation source that is 1.39 to multiply to 10 to the power of 9 meter in diameter. That's the diameter, and is located 1.5 multiplied by 10 to the power of 11 meter away from us. It emits approximately as a black body, as it's a black body. So we consider Sun as a black body at a temperature of 5,780 Kelvin. Okay, more or less at the same temperature. But how we calculate that temperature, we are going to speak about it, or how we can be sure that the surface temperature of the Sun is around 6,000 Kelvin, or to be exact 5,780 Kelvin. But as the radiation emitted by the Sun, it travels through the space, okay? But we said that, okay, for example, the radiation is the only form of heat transfer happens in vacuum. Okay, so from the Sun to the like outer surface and atmosphere, it's okay, more or less. We can say that there is no problem because it goes through the vacuum. But of course, the radiation will decrease because of the factor which is determined by the radius of the Sun as well as the distance, because we are located far from the Earth. We are not going to go through that concept, but the only thing that we need to get is GS, which is solar constant. We are not going to go through what will happen between Sun and the outer surface and atmosphere. What we need to know is how much gets to the outer surface of atmosphere. It's GS, and of course they have calculated which GS is equal to 1,373 watt a square meter. Okay, what is happening here from the Earth? From the Sun, sorry. What is happening between Sun and the outer surface of the atmosphere is not our interest. The only thing that we know that the GS, which is the solar constant, is a constant number, and the number is 1,373 watt per square meter. Okay. But what is this solar constant? This solar constant is the total solar irradiation at the outer surface of the Earth's atmosphere. Okay, so at the outer edge, or like a surface of the Earth's atmosphere, the total solar irradiation is equal to 1,373 watt square meter. In the previous slide, I mentioned that the Earth temperature is 5,780 Kelvin. But how we get to that number? If you remember, I just said that we can consider Sun as a black body. Okay, so we said that, okay, it's black body. What does it mean, black body? It means that we can calculate the total energy that leaves the Sun's outer surface. Okay, how? We can say that A sigma T4. So 4P R2 sigma T Sun to the power of 4. This is the Sun radius. Okay. So this one is the total energy that leaves the Sun's outer surface. So the conservation of energy says that since the solar radiation goes through the vacuum, the amount of energy leaves the Sun must be equal to the solar energy passing through the spherical surface with the radius of L, which L is the surface between Earth and Sun. Okay, does make sense? So basically 4P L2 solar irradiation is equal to the total energy that leaves the Sun surface, sigma t sun to the power of 4. This L, we just said that we know that it's 1.5, the Earth is 1.5 multiplied by 10 to the power of 11 meter away from us. We said that we know the radius of the Sun is 1.39, 10 to the power of 9 meter. We also said that we know the solar constant 1373 watt a square meter. So what else left? We know the Stefan Boltzmann constant. The only thing is left is T sun, and we can calculate it, and it will be 5780 Kelvin. That's how we calculate the Sun's surface temperature. Let me go back to this slide. If you remember, like just 5 minutes ago, we discussed about the effect of absorption by the atmospheric gases. But as a result of those absorptions, solar energy is not as weak when, as strong when it reaches the Earth's surface. Okay, so we said that the GS, which is the solar constant, is 1373, to where it's at the outer edge of the Earth's atmosphere. But we are not going to get all of that, because when it goes through the atmosphere, because of the absorption, because of the scattering, lots of that energy will be gone. So we are not going to receive that one. But we talked about absorption, that they are molecules in atmosphere that they absorb energy. Beside absorption, there is another mechanism that will affect the solar radiation while it passes through the atmosphere. This mechanism is called scattering or reflection. Simply, it means that the solar radiation before reaches the Earth's surface will be absorbed and scattered by air molecules, as well as other kind of particles in the atmosphere, like dust, smoke, water droplets, whatever. Okay, so scattering is mainly governed by the size of the particle reflecting to the wavelength of radiation. Okay, we know that the 80% of the Earth atmosphere consists of oxygen and nitrogen molecules, and nitrogen and oxygen primarily they scatter radiation at very short wavelength, and that's the reason why the sky looks blue or bluish to our eyes. Why? Because 80% of the atmosphere consists of oxygen and nitrogen molecules primarily scatter radiation at very short wavelength. Short wavelength means blue and violet. Okay, and that's like a kind of maybe a response why sky looks bluish. So the incident solar energy on the surface on the Earth consists of two parts, direct and diffuse. Okay, so if you remember, first we said that okay, this is sun, we don't care what is happening between, but it reaches to the Earth. At the outer surface of the Earth is GS, which is equal 1373 watt a square meter. Between and after that, we said that okay, this is the outer edge. Between the outer edge and the Earth, okay, there is like a atmosphere. This atmosphere, due to absorption and scattering, will reduce the amount of energy that we receive. And now we are talking about the solar energy on the surface of the Earth. So basically, we are saying that what we are receiving on the surface of the Earth, G solar, is equal to GD cosine theta plus GD. This one we call it direct solar radiation, and G with a small d is diffuse solar radiation. So diffuse solar radiation is a proportion of the total solar radiation that varies based on the weather. In a clear day it's around 10% and can be neglected, but in a cloudy day it's around 100% of the total solar radiation. So it depends to the weather. We can't say anything about it. For different weathers we need to calculate it, okay? But let's find the net rate of radiation heat transfer to a surface exposed to a solar and atmospheric radiation and finish this section. So let's say we have this situation: the sun, G solar, goes to the Earth, and after that atmospheric, G sky as well. Now we want to know that what is the like a net rate of radiation. So I want to know the Q dot net rate of radiation. So simply I can say that it's like a sigma of all absorbed minus all emitted. Can I say that? I think it's acceptable. What the surface is receiving? It's receiving alpha S G solar. It's also receiving epsilon G sky. But why emissivity? We will talk about it because of the picture. Sky. But based on the Krishov's law is alpha, so it doesn't matter basically, minus the emitted. The emitted energy will be epsilon sigma T S to the power of 4. So basically that's a net rate of radiation heat transfer. So sometimes we can have the convection heat transfer rate as a losses parts as well, because it will consider as a loss energy. Let's say this is Q net is, if we want to make it much easier for us to, so it's alpha G solar, as I told you, based on the Krishov's law. Instead of alpha we can put epsilon, so epsilon G sky, which is sigma T sky to the power of 4 minus epsilon sigma T S to the power of 4. So it's alpha G solar plus epsilon sigma T sky to the power of 4 minus T surface to the power of 4. That's a net rate of radiation heat transfer. So of course if we don't have any loss due to convection, okay? But let's solve one example and see how we can implement it into a question. This is question 12.96 of your textbook. As you can see, the absorbed surface of a solar collector is saying that is made of aluminium coated with black chrome, so of course opaque surface. We have the absorptivity, we have emissivity. Solar radiation is incident on the surface, at the rate of 600 watt per square meter. The air and the effective sky temperature are 25 and 15 respectively, and the convection heat transfer coefficient is 10. For an absorber surface temperature of 70, determine the net rate of solar energy delivered by the absorber plate to the water circulating behind it. Determine the equilibrium temperature of the absorber surface if the black side of the absorber is insulated. Okay, so we have the alpha S, we have epsilon, we have G solar, we have T air, we have T sky, we have H, which is heat transfer coefficient. We also have Ts, which is 70 degrees. Okay, so what we need to find is the net rate of solar energy, Q dot net, and we also need to find that determine the equilibrium temperature of the absorber surface if the black side of the absorber is insulated. So first we need to find the Q dot net, and in the second part we need to say that okay, Q dot net is equal to 0. By knowing that, we need to find the Ts. What would be the Ts? So of course, if the Q dot net is equal to 0, Ts won't be 70 anymore. Okay, let's start. So Q dot net, I can basically write is like all the gains minus all the losses. Okay, so what are the gains? Alpha S G solar plus previously like exactly like a previous example, epsilon sigma T sky to the power of 4 minus epsilon sigma Ts to the power of 4 minus H Ts minus T air. So there are 2 gains and 2 losses, 1 convection and 1 solar. So if we want to put it, it will be alpha S G solar plus, or we can say minus, we can put everything together, this epsilon sigma Ts to the power of 4 minus T sky to the power of 4 minus, or plus H Ts minus T air. So we have G solar, yes, 600, we have it. We have alpha S 0.87, we have epsilon 0.09, Stefan Boltzmann constant, we have it. Ts we have 70, T sky we have 15, but you know that you need to convert it into the Kelvin. H, we have the H, which is 10 watt to Kelvin. Here Ts we have at 70, and T air we have at 25 degrees. So we have all the information. The only thing that we need to do is using the calculator. The final answer, the Q dot net, will be equal to 141 watt a square meter. Okay, so that's the first part. The second part is saying that if the backside of the plate is isolated. So it's saying that if q.net is equal to 0, find Ts. So basically what we need to do is alpha S G solar is equal to epsilon sigma Ts to the power of 4 minus T sky to the power of 4 plus H Ts minus T air. Okay, T air we have at 25, Ts we don't need, we need to find it, we can't use this 70. The 10 we have it, 10 watt there Kelvin. T sky we have it, 15. As we need to find sigma is a Stefan Boltzmann constant. Epsilon we have it, 0.09. Here alpha S we have it 0.87, and G solar we have it 600 watt square meter. If we put everything together and we use our calculator, the final answer, the Ts will be 356 Kelvin. Okay, that was the end of our third lecture. Thank you for your attention. Please go through the lecture maybe 2 times if you don't understand it the first time, and at the end, if you went through your textbook, you went through the lectures 2 times and you didn't understand, you are more than welcome to drop me an email and I try to explain it to you. Thank you.